Trusses also experience live loads, so an influence line can be a valuable tool for presenting information about the effect of live load on the member of a truss. So in this problem, we're going to construct an influence line for a single member of a truss using the basic method, or the table of values method, and we'll use that influence line to find the maximum effect of live loading. Now we can't use the Mueller-Breslau principle in this case because it doesn't apply to trusses. Key concepts we'll use are calculating truss member forces using the method of sections, constructing an influence line from values at certain points, and using an influence line to determine the maximum possible internal loading. And here's our truss. We want to construct an influence line for the member CF. We then want to compute the maximum live force, tension, or compression that can be developed in that member due to a uniform live load of 800 pounds per linear foot, which is transmitted to the truss along the bottom chord, that is along A, B, C, D, E. Now our approach. We'll start by deciding locations to apply the unit load. Then we'll apply the unit load one at a time to each of those locations. And we'll calculate the force in member CF. We'll then be able to construct the influence line from those points. Then we'll apply the live load to maximize the force in member CF. Let's begin. Step 1. Decide where to apply the unit load. Now the key is to make sure we apply it in enough places to generate sufficient information to construct our influence line. If we look at more points than we need, it's additional information and it takes us a little bit longer, but it won't hurt. If we miss an important point, it'll change the shape of our influence line. In this case, we're going to apply the unit load at B, C, and D. We're going to skip A and E because when a force is applied at the supports, there's no load generated anywhere in the truss. Now step 2. Apply the unit load and calculate the force in member CF. And we'll start with the unit load at point B. We have our reaction AY, our reaction EY, and we'll sum moments about point E. We'll choose clockwise as positive. It's our choice which direction we choose as positive, but that makes my unknown AY in a positive rotation at 40 feet, the unit load in a negative rotation through 30 feet. Solve that for AY and we get a positive 0.75 in the direction we drew it. Now I'm ready to cut the truss, and I'll cut it at panel CD. Remember, method of section says that we can only cut 3 unknown truss members, and we have to cut it into 2 distinct sections of truss, and ideally we'll cut the member we're looking for, in this case member CF. I'll keep the left piece. We have our vertical reaction, 0.75, up. We have our unit load, 1, down. We have our unknown force in member CD, our unknown force in member CF, the one we're looking for, and unknown force in member GF. Now to apply equilibrium, we're going to need to look at the slope of member CF. The rise to run ratio is 1 to 1, which means the hypotenuse would be square root of 2. Let's sum forces in the vertical direction. Choose up as positive. We get the reaction at A. Subtract the unit load, and we get only, of the 3 unknown forces at the cut, a component of CF, and it is going to be 1 over the square root of 2 times the force in CF. Solve that for the force in member CF, and we get 0.354. And that's positive, so that'll be tension when the unit load is applied at B. Now we move the unit load to point C. We have the vertical reaction AY, vertical reaction EY. Once again, we sum moments about point E, and we choose clockwise as positive so that our AY reaction acts in a positive direction through 40 feet. Our unit force acts in a negative direction through 20 feet. AY must be a positive 0.5 in the direction drawn. Now we'll cut the truss into 2 sections, and we'll cut it at panel CD, just as we did before. I'll keep the left free body diagram, or the left section for my free body diagram. I have my reaction at A, my unit load at C, my unknown forces in the truss members at the section cut, and again I will sum forces in the Y direction, so only member CF contributes of the 3 unknowns. We have the 0.5 reaction at A, the unit load in a negative direction, 1 over the square root of 2 is the component of CF in the vertical direction. And that gives us a force in member CF of a positive 0.707 when the unit force is applied at point C. Now we move the unit load to point D. The vertical reaction EY, vertical reaction AY. We sum moments about point E, some positive in the clockwise direction. AY acts through 40 feet. The unit force acts in the opposite direction through 10 feet. AY is a positive 0.25 in the direction drawn. We'll cut the truss into two sections at panel CD. I'll keep the left section. We have the vertical reaction at A. The unit load is now at D, so it's not on this free body. We have our unknown truss member forces, and only FCF is in the vertical direction. So we sum forces in the Y, choose up as positive, get the contribution from the reaction at A, the contribution from member CF, and that's it. Solve for the force in member CF. We get a negative 354, or compression of 0.354, when we have a unit load acting at point D. So now we have all the information we need to construct the influence line. We'll start by tabulating the results we have. The location of the unit load and the resulting force in member CF. Although we didn't calculate it, we could have, but when the unit load is applied at point A, it's directly into the support and there'll be no loads generated inside the truss. So that one's 0. At B, we found a positive 0.354. At point C, a positive 0.707. At D, a negative 0.354, so it goes into compression. And at E, we'll find that we're back to 0. So we can now construct our influence line by plotting the points. At A, there is no force generated in member CF. At B, we get 0.354. At C, we get 0.707. At D, we get a negative 354. And then at E, we're back to 0. It's a determinate truss, and so each of these points must be connected by straight line segments, and we get an influence line that looks like so. Now notice that the point where the influence line goes 0 is not at a joint in the truss. So let's figure out how far from point C the influence line becomes 0. And we'll use similar triangles. That distance over the magnitude of the influence line at that point has to be the same as this distance, which is 10 feet minus x, over this height, which the absolute value is 0.354. Well, if I cross multiply, I'll get a 0.354. X is 7.07 feet minus a 0.707 x. Put those all together and we find that x is 6.67 feet. Since we constructed the influence line, minus 0.354, positive 0.707, and we know this distance is 6.67 feet, we can now begin step 4, which is to locate where to apply the load to maximize the force in member CF, and then we'll actually apply that load and calculate the maximum. Now as we look at these areas under the influence line, we have a very large positive area and a smaller negative area. It's the area under the influence line that tells us where to put the load in order to maximize the effect. And since the positive area is much larger, the maximum force in CF will be tension. If the negative area was larger, then the maximum force in CF would have been compression. So let's find the maximum force in member CF. To do that, we apply our distributed load over the bottom chord of the truss wherever the influence line is positive. So all the way up to this point, which is 26.67 feet from point A. So the area underneath our influence line, it's a triangular area. We have 1/2, peak value 0.707, the base of that triangle 26.67 feet, and the magnitude of the distributed load 800 pounds per foot. We solve that. 7,540 pounds, and that is in tension. Now let's go back and review how we got to this point. We started by identifying where to apply the unit load so that we could generate enough information to construct our influence line. We saw that we only needed to apply the unit load in 3 places, B, C, and D, because at A and E we knew that the force generated in all of the members would be 0. Then in step 2, we started applying the unit load and calculating the force in member CF. So we started at point B, found a tension value for force in member CF, moved that unit load to point C, and we got an increasing tension value in member CF. But then as the force passes member CF and moves to point D, the sign changes to negative, so we get compression in member CF. We then consolidated all of that information into a table, plotted the points, connected them with straight lines, and then we calculated where the influence line became 0, because that would be important to us as we approach step 4, which is maximizing the force in member CF due to a uniform distributed live load. We looked at the 2 areas under the influence line, a positive area and a negative area. The positive area was much bigger, and so we applied the distributed load over the region where the influence line is positive, then applied that distributed load, calculating the resulting force in member CF, and found 7,540 pounds in tension. Well done.